Welcome to this coding walkthrough. In this session, we'll tackle the problem Find Peak Element. We'll explore an efficient way to solve this and review key takeaways at the end. Let's get started. The problem requires us to find a peak element in an array. A peak element is defined as one that is strictly greater than its neighbors. For instance, in a zero-indexed array, if an element at index I is greater than both nums, I1, and nums, I+1, then it qualifies as a peak. If the element is at the boundary of the array, it only needs to be greater than its single valid neighbor. To simplify the problem, we can imagine that the elements outside the array, nums-1, and nums-n, are set to -infinity, ensuring that boundary elements have a well-defined comparison. The task is to return the index of any peak element, and if there are multiple valid peaks, any one of them is acceptable. The input array must have a size between 1 and 10 to the power of 5, and all elements are unique integers within the range of -2 to the power of 31 to 2 to the power of 31 1. Finally, the output is just the index of one peak element. To understand this better, let's look at the first example. For the input nums equals 1, 2, 3, 1, the output is 2. This is because the element at index 2 is 3, which is greater than both its neighbors, nums 1 equals 2 and nums 3 equals 1. Therefore, the index 2 is returned. Now, in the second example, the input is nums equals 1, 2, 1, 3, 5, 6, 4. Here, one valid peak is at index 5, where the element is 6. It is greater than its neighbors, nums 4 equals 5 and nums 6 equals 4. Another valid peak is at index 1, where the element is 2. It is greater than its neighbors, nums 0 equals 1 and nums 2 equals 1. Since the problem allows any valid peak index to be returned, the function can return 1 or 5. These examples help illustrate how the definition of a peak works in practice. There are a few edge cases to consider. First, if the array contains only a single element, that element is automatically a peak since there are no neighbors to compare it to. For example, in nums equals 10, the peak is at index 0. Next, in a strictly increasing array like nums equals 1, 2, 3, 4, the last element is the peak because it has no neighbors on the right and is greater than all preceding elements, so the output is 3. Similarly, in a strictly decreasing array like nums equals 4, 3, 2, 1, the first element is the peak, making the output 0. Lastly, if there are multiple peaks in the array, such as in nums equals 1, 3, 2, 4, 3, the function can return the index of any one of them. In this case, valid outputs include 1 or 3. These edge cases highlight the flexibility of the problem and the scenarios you might encounter. To solve the problem of finding a peak element, one straightforward approach is to use brute force. The intuition here is simple: a peak element is one that is greater than its neighbors. By iterating through the array, we can check for each element whether it satisfies the peak condition. Specifically, for an element at index I, we check if it is greater than its left neighbor, if one exists, and its right neighbor, if one exists. If these conditions are met, we immediately return the index as the peak. While this approach is easy to understand and implement, it comes with a trade-off. Its time complexity is O(n), as we potentially examine every element in the array. This linear time complexity can become a limitation for larger arrays. On the positive side, it has O(1) space complexity since no additional memory is required. However, it does not take advantage of the properties of the problem, which guarantees the existence of a peak and allows for more efficient solutions. A more efficient approach utilizes binary search, leveraging the problem's guarantee of a peak element and the ordered nature of the comparisons. Here's how it works: if the middle element of the array is less than its right neighbor, it means there must be a peak on the right side, as the slope is increasing. Conversely, if the middle element is not less than its right neighbor, then a peak must exist on the left side, including the middle element itself. Using this insight, we initialize two pointers, low and high, to the start and end of the array. While low is less than high, we calculate the midpoint and compare the element at mid with its right neighbor. Depending on the comparison, we either shift the low pointer to mid +1 or the high pointer to mid, thereby having the search space in each iteration. Once the pointers converge, we return their position as the peak index. This approach has a time complexity of O log n, since the search space is reduced by half each time, and a space complexity of O(1), as no additional memory is used. The trade-off here is that while it is faster, it requires a slightly more complex implementation. An alternative to the iterative binary search is a recursive binary search approach. The intuition remains the same. We use the relationship between the middle element and its neighbors to decide whether to search the left or right half of the array. Instead of using a loop, we define a helper function that takes low and high as parameters and calls itself recursively until the base case is reached, where low equals high. At each step, we calculate the midpoint and compare the element at mid with its right neighbor. If the mid element is less than its right neighbor, we recursively search the right half of the array, passing mid plus 1 and high as the new bounds. Otherwise, we search the left half by passing low and mid as the new bounds. Once the base case is reached, the function returns the position of the peak element. This recursive method has the same time complexity as the iterative binary search, O log n, but with an additional space complexity of O log n, due to the function call stack. While it may be more intuitive for those comfortable with recursion, it has the downside of using more memory compared to the iterative approach. Given these options, the iterative binary search approach is the chosen strategy for solving this problem. The key insight that drives this choice is the guarantee of a peak element. By observing the relationship between the middle element and its neighbors, we can conclusively determine whether to search the left or right half of the array, reducing the search space logarithmically. If the middle element is less than its right neighbor, moving to the right ensures that a peak exists in that direction due to the increasing slope. Otherwise, moving to the left includes the possibility of a peak at the midpoint or earlier. This method's logarithmic time complexity makes it significantly more efficient than the brute force approach, which has linear complexity. Additionally, the iterative version is preferred over the recursive alternative due to its constant space usage, avoiding the risk of stack overflow in scenarios involving very large arrays. While the iterative implementation may require more careful handling of boundary conditions, its efficiency and robustness make it the optimal choice for this problem. In considering the trade-offs, the iterative binary search method stands out as the most efficient and scalable solution. Although binary search requires a more thoughtful implementation compared to brute force, the logarithmic performance gain justifies the added complexity. By avoiding the additional space cost of recursion, the iterative approach achieves constant space complexity while maintaining logarithmic time complexity. This combination of optimal time and space efficiency makes it well suited for handling large datasets. In conclusion, the iterative binary search method addresses the problem requirements effectively, balancing performance and implementation considerations, and is ultimately the most practical solution for finding a peak element. In this problem, you are given an array of integers where a peak element is defined as an element that is strictly greater than its neighbors. The task is to find the index of any one peak element. It's important to note that the array can have multiple peaks, and neighbors are defined as the elements directly adjacent to the current one, if they exist. For example, in the array 1, 2, 3, 1, the element 3 is a peak because it is greater than both of its neighbors, and its index is 2. One approach to solving this problem is the brute force method. The intuition here is straightforward. Since a peak element must be greater than its neighbors, we can simply traverse the array and check each element to see if it satisfies this peak condition. While this approach guarantees a solution, it is not the most efficient way to solve the problem, as we'll see shortly. To implement the brute force approach, start by initializing a loop that iterates through the array from index 0 to len nums 1. For each element nums I, you evaluate its neighbors based on its position in the array. If I is 0, meaning it's the first element, check if it's greater than its neighbor nums I plus 1, if that neighbor exists. Similarly, if I is the last index, check if it's greater than its left neighbor nums I1, if that exists. For all other indices, check if nums I is greater than both its left neighbor nums I1 and its right neighbor nums I plus 1. If any of these conditions are satisfied, you return the index I as the peak. Since the problem guarantees the existence of at least one peak, there's no need to handle cases where no peak exists. However, if implemented incorrectly, you might end up returning -1. While this method is simple, we can optimize it further using binary search. To optimize the solution, we use a binary search approach. Start by initializing 2 pointers, low at 0 and high at len, nums, 1, representing the search range. While there is more than one element in this range, calculate the middle index mid is, low plus high, / 2. Then, compare the element at mid, nums, mid, with its right neighbor nums, mid plus 1. If nums, mid, is greater than nums, mid plus 1, it means there must be a peak in the left half of the array, including mid, so you set high equals mid to narrow the search range. Otherwise, if nums, mid, is less than nums, mid plus 1, it means there must be a peak in the right half of the array, excluding mid, so you set low equals mid plus 1. This process continues until the search range contains only one element, at which point low and high will be equal, and this single element is guaranteed to be a peak. You then return the index low, or equivalently high. There are a few key insights that make this algorithm both efficient and reliable. First, a peak is guaranteed to exist in any array due to the finite nature of the array and the fact that the edges of the array can act as boundaries for peaks. Second, the binary search approach works because if nums, mid, is not a peak, the direction of the larger neighbor ensures the existence of a peak in that direction. This property allows us to confidently eliminate half of the array in each iteration without missing a potential peak. Additionally, it's important to consider edge cases. For a single-element array, the sole element is trivially the peak. For a two-element array, the larger of the two is the peak. Peaks at the boundaries are also handled correctly because we explicitly check the neighbors conditionally. Finally, this algorithm uses only the input array and simple variables like low and high, so it doesn't require additional data structures. When analyzing the complexity of these approaches, the brute force method has a time complexity of O(n), where n is the length of the array, because in the worst case, you may need to check all elements once. Its space complexity is O(1), since it doesn't use any additional memory. On the other hand, the binary search approach is much more efficient. Its time complexity is O log n, because the array size is halved in each iteration of the search. Similarly, its space complexity is also O(1), as it only uses 2 pointers and a few variables for computation. Let's walk through an example to see how binary search works. Given the input nums equals 1, 2, 3, 1, we start with low equals 0 and high equals 3. The middle index is calculated as mid equals 0 plus 3 / 2 equals 1. Compare nums 1 equals 2 with nums 2 equals 3. Since nums 1, nums 2, we move to the right half by setting low equals 2. Now, low equals 2 and high equals 3. Recalculate mid equals 2 plus 3 / 2 equals 2. Compare nums 2 equals 3 with nums 3 equals 1. Since nums 2, nums 3, move to the left half by setting high equals 2. At this point, low equals 2 and high equals 2, so the search range contains a single element. Return 2, which is the index of the peak. Key optimizations in the binary search approach make it highly efficient. By leveraging the guaranteed existence of a peak, the algorithm avoids unnecessary checks or backtracking, focusing only on the direction where a peak is certain to exist. This eliminates half of the search space in every step, making it significantly faster than the brute force method, especially for large input arrays. Additionally, the simplicity of the algorithm, which uses just a few variables and no extra data structures, ensures minimal overhead. This combination of speed and simplicity makes the binary search approach the preferred solution for this problem. This solution uses a binary search approach to efficiently find a peak element in the array. Here's how it works. The function starts by initializing 2 pointers, left and right, to represent the bounds of the search space. Left is set to the start of the array, index 0, and right is set to the end of the array, index len, nums, 1. The main logic is contained in a while loop that iterates as long as left is less than right. Inside the loop, the midpoint of the current range, mid, is calculated using integer division to avoid fractional indices. Next, the algorithm compares the value at the midpoint, nums, mid, with the value of its right neighbor, nums, mid plus 1. If nums, mid, is greater than nums, mid plus 1, it means the peak lies on the left side of the array, including the current mid, so the right pointer is updated to mid. Otherwise, the peak lies on the right side, and the left pointer is updated to mid plus 1. This process continues, progressively narrowing the search space until left equals right, at which point the loop terminates. Since the algorithm guarantees that the peak lies within the narrowed range, the function returns the index left, or equivalently right, which points to a peak element. This binary search approach runs in O log n time complexity, making it highly efficient for large input arrays. The algorithm ensures correctness by leveraging the properties of the input array, where a peak always exists due to the problem constraints. This is the Java implementation for LeetCode problem number 162, find peak element. The logic mirrors the provided Python solution, using a binary search approach to efficiently locate a peak element. Key differences include Java-specific syntax, such as explicit type declarations and the use of a while loop with index bounds. The method iteratively narrows the search range based on comparisons between the middle element and its neighbor, ensuring O log n complexity. Here, we begin by examining the array nums equals 1, 2, 3, 1. Initially, our left pointer is set to 0, and the right pointer is at 3, which corresponds to the last index of the array. In the first iteration, we calculate the middle index using the formula mid equals left plus right / 2, giving us a mid value of 1. At index 1, the value is 2, and we compare it with the value at index 2, which is 3. Since 2 is less than 3, we conclude that the peak must lie on the right side of the array. Therefore, we adjust our left pointer to mid plus 1, which is 2. Now, in the second iteration, we recalculate mid as 2 plus 3 / 2, which gives us a mid value of 2. At index 2, the value is 3, and we compare it with the value at index 3, which is 1. This time, since 3 is greater than 1, we know the peak must be on the left side, including the current mid. Thus, we update the right pointer to mid, which is 2. At this point, the left and right pointers have converged, both pointing to index 2. This means the termination condition left equals right is met, and we know that index 2 is the peak. The value at this index is 3, so the function returns 2 as the output. Now, let's examine another example with the array nums equals 1, 2, 1, 3, 5, 6, 4. Initially, the left pointer is at 0, and the right pointer is at 6, the last index of the array. In the first iteration, we calculate mid equals 0 plus 6 / 2, which gives us a mid value of 3. At index 3, the value is 3, and we compare it with the value at index 4, which is 5. Since 3 is less than 5, the peak must be on the right side of the array. Therefore, we update our left pointer to mid plus 1, which is 4. In the second iteration, we now focus on the subarray from index 4 to index 6. We calculate mid equals 4 plus 6 / 2, which gives us a mid value of 5. At index 5, the value is 6, and we compare it with the value at index 6, which is 4. Since 6 is greater than 4, we determine that the peak must be on the left side, including the current mid. Therefore, we adjust the right pointer to mid, which is now 5. At this point, the left and right pointers both converge at index 5, meeting the termination condition. The function returns index 5 as the peak, and the value at this index is 6. So, the output for this example is 5. Finally, let's look at a simpler example with the array nums equals 1, 2. Here, the left pointer starts at 0, and the right pointer is at 1. In the first iteration, we calculate mid equals 0 plus 1 / 2, which gives us a mid value of 0. At index 0, the value is 1, and we compare it with the value at index 1, which is 2. Since 1 is less than 2, the peak must be on the right side of the array. So, we update the left pointer to mid plus 1, which is 1. Now, the left and right pointers both point to index 1, satisfying the termination condition. The function returns index 1 as the peak, and the value at this index is 2. Therefore, the output is 1 for this example. The time complexity of the binary search solution for finding a peak element is O log n, where n is the size of the input array. This efficiency comes from the binary search approach, which works by having the search space during each iteration. Initially, the algorithm starts with the entire array, and then it compares the middle element with its neighbor. Based on this comparison, it updates either the left or right pointer to focus on a smaller subarray. After the first iteration, the search space is reduced to half, or n/2 elements. After the second iteration, it's reduced further to n/4, and this continues until only one element remains. The number of iterations required to narrow the search space to a single element is proportional to the logarithm of n base 2, which gives us log_2, n. Since each iteration involves a constant amount of work, like calculating the middle index and performing comparisons, the overall time complexity is O log n. In the best-case scenario, the peak might be found on the first check, resulting in O1. However, in both the average and worst cases, the logarithmic reduction ensures the complexity remains O log n. This makes the binary search solution highly efficient compared to a linear approach. The space complexity of this algorithm is O1, meaning it uses a constant amount of extra memory regardless of the size of the input array. This efficiency is due to the fact that the algorithm only requires a few variables, such as left, right, and mid, to manage the search process. These variables take up a fixed amount of space, and no additional data structures like arrays or recursion stacks are needed. The algorithm directly accesses the input array without creating any copies or auxiliary storage. As a result, the memory usage remains minimal and does not grow with the input size. This constant space requirement is another key advantage of the binary search solution, as it ensures that the algorithm remains efficient in terms of memory usage, even for very large arrays. Now, let's compare the binary search approach with a naive method. The naive approach involves iterating through the array to check each element against its neighbors, which leads to a time complexity of O(n). This is because, in the worst case, it requires a linear scan of the entire array. However, the space complexity for the naive approach is still O(1), as it doesn't use any additional data structures. On the other hand, the binary search approach significantly improves the time complexity by reducing it from O(n) to O log n. This improvement comes from the logarithmic narrowing of the search space, which minimizes the number of comparisons needed. Both approaches share the same space complexity of O(1), but the binary search is far more efficient for large input sizes since it leverages the array's properties for faster peak detection. In summary, the naive approach has O(n) time in O(1) space, while the binary search solution achieves O log n time with O(1) space, making it the optimal choice for this problem, especially for larger arrays. When tackling the find peak element problem, there are a few common mistakes that can trip you up. First, failing to handle edge cases can lead to incorrect results. For example, if the array has only one element, that single element is the peak. Similarly, in a strictly increasing array, like 1, 2, 3, 4, the last element is the peak, while in a strictly decreasing array, the first element is the peak. Second, some assume that peaks are unique. However, the problem often allows for multiple peaks, and your goal is simply to find any one of them. Trying to find all peaks unnecessarily complicates the solution. Another frequent error is using linear search when the problem explicitly requires logarithmic complexity. This can result in time limit exceeded errors for large inputs. Finally, binary search implementations are prone to off-by-one errors. For instance, forgetting to properly check boundary conditions like nums, mid plus 1, can cause your solution to fail. Careful handling of indices is crucial for correctness. Another mistake to avoid is modifying the input array. Some approaches, such as sorting or marking elements, violate constraints and change the problem entirely. Always work with the input as is unless explicitly allowed to modify it. Now, from an interview perspective, there are a few key insights to keep in mind. Peak finding problems often rely on local properties, such as nums, I plus 1, which makes them perfect for divide and conquer or binary search techniques. Recognizing these patterns can guide you toward the most efficient solution. Additionally, analyze the constraints carefully. For very large arrays, brute force approaches are unlikely to succeed, so logarithmic solutions like binary search should be your go-to. Be prepared to explain why binary search is optimal. Highlight its O log n complexity and how it efficiently narrows down the search space. Lastly, always clarify the problem statement during interviews. Confirm whether the array is guaranteed to have a peak and whether finding any peak is sufficient. Misunderstanding the requirements can lead to wasted effort or incorrect answers. This problem is closely related to other variations that you might encounter. For example, LeetCode 852, peak index in a mountain array, involves finding the peak in an array with a mountain property, and LeetCode 1095, find in mountain array, builds on this with additional constraints. Another related problem is LeetCode 153, find minimum in rotated sorted array, which also uses binary search principles. Now, let's discuss alternative approaches to solving peak finding problems. The brute force method involves traversing the array and checking the peak condition for each element, where nums I1, and nums I plus 1. While this approach is simple to implement, its time complexity makes it inefficient for large arrays. On the other hand, binary search uses the property that if nums mid plus 1, a peak must exist on the right half, and if nums mid plus 1, a peak lies on the left half. This approach is optimal with log n complexity but requires careful index handling. Alternatively, you can implement binary search recursively for cleaner code, although this may risk stack overflow for very large inputs. A more specialized approach you might encounter is the modified sliding window technique, which can be useful in variations like circular arrays. This method adjusts the window dynamically to find a peak under specific constraints. However, it's important to note that this approach isn't universally applicable and is context-dependent. Understanding when and where to apply these methods is key to mastering peak finding problems across different scenarios. Great job making it through. To recap, we discussed the find peak element problem and reviewed the brute force approach. Remember to practice and explore optimized solutions like binary search. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!